Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 9, Python Graphics for Climate Science. In this video, we will create color contour maps. Let's begin with some basic principles for a Python contour plot. First, going into figure 9.2.1. So first, let's go ahead and set up the variables. Set up an x and y using that NP linspace from -1 to 1, and it's going to have a size of 25. Then let's also set up a z variable that is taken from the standard normal distribution. This size will be a ND array that has 25 columns and 25 rows. Next, let's go ahead and set up that figure using the Plt subplots. Now to the contour plot, we are going to go into that AX variable that we just created and create a contour F on variables X by Y by Z. We are going to use the CMap, which is the color map of jet. This CM1 get CMap just allows us to use a discrete color map on the jet color map rather than a continuous color map. Next, let's create and set some labels. We could go ahead and set our Y tick labels to those tick labels that we just created. Set our X tick labels to that variable we just created. Set our Y label, set our X label, and setting our title. Lastly, wrapping our block of code with a color bar function on the myMap function, which is the contour plot itself. Lastly, wrapping it in a fig.show, we do get this filled contour plot of normal random values to pop up. We do have a discrete color map with a -1 to 1 on the y-axis as well as the x-axis. Now let us plot contour color maps for random values on a map. This figure corresponds with figure 9.6 in the book. We are plotting a 5x5 grid of global map on the standard normal random values. First, let's set up our variables. We have our lat range and our long range representing latitude and longitude on this map. We are going to create the data that's going to be plotted, taking it from the standard normal distribution with the size that has rows the same size as that lat variable and columns the same size as that long variable. We are also going to create some levels on which we want our contour color bar and contour plot to abide by. Now setting up our figure using that Plt subplots, we are specifying our fig size in this case. Then going into our subplot, naming this variable AX, and this is going to be in position 1 with row and column equal to 1 as well. We are going to use the projection from the Plt carré function with a central longitude of 180 degrees. This will allow that central longitude to be 180 degrees on our map that is projected. We are going to allow our coastlines to be visible on this map as well. We're going to use that set global function to help us ensure that we see the entire map, and our set title to make sure we give our plot a title. We are going to create a desired color map, not a pre-made one. We are using this array of colors. Then we are going to reverse that array of colors and use a function called newCallMap on that colors array. This variable will be named myCallMap. Next, we're going to plot the data We are using that contour F function once again. On our longitude, we are actually going to be using long minus 180 because we want it centered at longitude of 180. Combining that second parameter with lat, and we are mapping our map mat onto our longitude latitude grid with the specified levels as dictated above, using that created color map that we created above. We do want to add some labels and our color bar to our plot using that Plt color bar on our contour variable. We are drawing our edges and we are setting our aspect to 12. We are going to set our ticks on our color bar to the integers from -3 to 4. We're going to go ahead and make some changes to our X ticks, setting our X tick labels to those that are specified, setting our X label to longitude, setting our Y ticks to -50, 0, and 50, and setting our Y label to latitude. Wrapping that whole block of code in a fig.show, we do get this standard normal random value plot to pop up. We could see that we have this specified color map, as well as having a superimposed world map under our contour plot. I would like you to also notice that we do in fact have longitude equal to 180 as our center in this map. Moving on to figure 9.7, we are going to be plotting a 5x5 grid regional map to cover the US and Canada. Let's go ahead and set up our variables. We're going to set up a lat3 variable that is going to represent our latitude, a long3 variable that represents our longitude, and our map dat, which represents the standard normal data that we are going to plot on our contour map. Setting up that figure using that Plt Subplots function, we can now go into the subplot dictated by row 1, column 1 in the index 1. We are using that plate carré to set up our map. We're going to set our extent to 230, 295, 10, and 65. We're going to add some coastlines to our plot. We are going to add the features that we want our state borders to show up on our plot. Set our title to standard normal random values, and now we can plot our data using that contour F function on our longitude, followed by latitude, followed by our data matrix, followed by the levels at which we want to plot this contour map, and lastly dictating our specific color map to be used. Then we are going to add some color bars and labels plotting the color bar using the Plt color bar function on our contour item. We're going to draw edges and have that aspect set equal to 12. We're going to set our ticks and set the aspect equal to auto. Lastly, going through our Y tick labels, our X ticks, and our X tick labels in the highlighted text. We are also going to use this new function called tick parameters. We're going to set this tick parameter with a length of 9. This allows our ticks on either axis to be a little bit longer than standard. Wrapping that whole block of code in a fig.show, we do get this standard normal random values plot to pop up. We do have our unique color map on the right side of our screen. This plot shows Canada and US with standard normal random values superimposed on it. Moving on to section 9.2.3, we're going to be plotting contour maps from the climate model data in NetCDF files. We're going to go into that dataset function in the NetCDF package and go ahead and import air.mun.mean.nc. We're going to call this data mat. Now we're going to prepare some data for plotting. We're going to enter that data, grab the variable long, and name it long to represent longitude. A similar method is used for latitude. Same thing happens for time and for the pre-CNC variable that is highlighted on the screen. Going into figure 9.8, we're going to set up that figure using the Plt subplots with a specified fig size. We are just going to plot the data using the regular plotting function with x value ranging from -90 to 90, which has the same size as the pre-CNC variable that was created in the block above. Then we are going to plot our pre-CNC, setting our color and the line width that we are going to be using. Now we could go into the labels and ticks. We're setting our Y label to temperature degree C, setting our Y ticks to 10 times I, where I is ranging from -3 to 3, setting our X label to latitude, setting those X ticks, setting our title, and our tick parameters. We do get this plot to pop up once running that block. 90 south by 90 north, temperature degree C along the meridial line at 160 degrees east on January 1948. Moving on to figure 9.9a, we are going to compute and plot the climatology and standard deviation for January 1984 to December 2015. First, we need to set up the variables for our map and the number of colors that correspond to the data values. This will be a contour levels. We are going to have our contour levels spanning from -50 to 50 with 81 values between them. My col map is now going to be created by the linear segmented color map from a list function. We are naming it my list, and our colors to be used are black, blue, dark green, green, white, yellow, pink, red, and maroon. We are also setting an N equal to 100, so this color map will look like a smoother gradient between the colors that are highlighted on the screen. We need to set up a January month variable using the highlighted text. Now we are going to take the standard deviation and name it SDMAT so we can plot this new variable. We're just accessing the NumPy standard deviation function and using it on the pre-CNC with access equals 0. Next, we're going to create our climatology matrix and name it ClimMat using the means of the January month variable we created above. Setting up two different levels for each plot that we are going to be looking at. Levels 1 is going to be range from -50 to 50 with 81 values in between, and levels 2 is going to range from 0 to 20 with 81 values in between. Setting up our figure using that Plt subplots, accessing the first subplot in our subplots, setting our central longitude equal to 180 in that plate carré function. We do want our coastlines to show, and we do want to set our title to NCEP RA 1948 through 2015 January Climatology. We're going to plot our data using that contour F with first parameter equal to long minus 180, second parameter equal to lat, third parameter equal to the Climat matrix, and we are going to be using the levels 1 variable on the specified myColMap that was created above. We're going to go through and add our color bar using the Plt color bar. We are not going to have any ticks and the aspect set equal to 12. We are going to set our ticks on our color bar to 20 times I for I in the range from -2 to 3. Set the aspect equal to auto, specifying our Y tick and our Y label. Next, going into our X ticks and our X tick labels and setting our X label. Lastly, setting those tick parameters with a length of 9 and a width of 1, wrapping the whole block of code with a fig.show. We do get this plot of the NC EPRA 1948 through 2015 January climatology. Moving on to figure 9.9b, we're going to plot the standard deviation that we retrieved in the block above. First, we just need to set up that figure using the Plt subplots. Then, accessing that first subplot, we are going to make the projection equal to the plate carré with central longitude equal to 180. We do want coastlines to show. We're going to set our title to make sure that we understand that this is the standard deviation. And now we are ready to plot our data using that contour F function. Rather than the Climat matrix as our third parameter, now we are using that SD mat matrix as our third parameter. Also using the levels 2 rather than the levels 1. We're going to add our color bar and labels. The highlighted text does have the same style and methods used in the plot above for setting your color bar, your Y ticks, and your X ticks. Then wrapping that in a tick parameters function, specifying a length of 9, a width of 1. And now we can show and save our figure in one function using a save fig function. We're going to name this saved figure Chapter 9 January std.jpg. When we run that block of code, we do get this beautiful standard deviation of the NC EP 1948 through 2015 January SAT RAs. Next, we are going to plot the data for displaying climate features. Moving into figure 9.10, we're going to plot the January 1983 temperatures using the above setup. We're just going to take that Climat matrix that we created above and go ahead and set it equal to the myMap mat. We're going to set up our figures, same method as in the previous plots, using that Plt subplot with our projection to allow us to have a central longitude of 180. Adding some coastlines, setting our title to January 1983 surface air temperature degrees C. Next, we can plot the data using that contour function on longitude minus 180 by latitude, and we are plotting the map matrix on levels 1 using that specified myColMap as our color map. Next, we are going to add our color bars and labels. The highlighted text is very similar as in the above plots. First, we add our color bar, then our Y ticks and labels, then X ticks and X labels. We are going to add a little bit of text to this plot just right above our color bar, and it will be degree C. Setting those tick parameters and wrapping our whole block with a fig.show, we do get this January 1983 surface air temperature plot. Moving on to figure 9.11, we're going to plot the January 1983 anomaly from the NCEP data. First, we're going to create our variables using levels 1 spanning from -6 to 6 with 81 values in between. We are going to make an anomaly matrix and name it ANO map. We are going to take our pre-CNC slice of our original data and minus our climatology matrix from that pre-CNC matrix. We're going to suppress our values into a -6 to 6 range using the following for loop. Next, setting up our figure using that Plt subplots just like above. Accessing that subplot, setting our central longitude equal to 180, adding coastlines, adding some state borders to our plot, and also setting our title. Now we can go into the contour map itself and name it cont f using that contour f function on the values longitude -180, latitude, and we are going to be plotting our ANO map, which is our anomaly matrix, using the levels 1 and the color map dictated by my col map. Once again, just adding those color bars and labels just as above, also adding a degree C over the color bar and setting our tick parameters. We do get this beautiful January 1983 surface air temperature anomaly plot to pop up. We can see that we did truly suppress our values in between 6 and -6, and we do in fact have a central longitude equal to 180. Moving on to plot the January 1983 temperature anomaly from the NCEP data, we are going to go in to creating figure 9.12a. First, we need to create and prepare our variables. We're going to make a mySlice, which will be the range from 0 to 144. We're going to make an ANO mat from our original ANO map using all rows, but only using the columns dictated by mySlice. For our level variable, we're going to set up int1 equaling to the line space between -6 and 6. Setting up that figure using that Plt subplots. Going into that first subplot, setting our central longitude equal to 200, plotting our coastlines and setting our title. Next, we could go into the contour map itself with first parameter line -180, second parameter lat, and third parameter ANO map with levels equal to int1 and our color map equal to my col map. Going in, adding the color bar and labels just like we did in the previous plots. Finally, adding a little bit of text right over that color bar and wrapping that whole block of code with a fig.show. We do get the January 1983 surface air temperature anomaly. Now, for the next plot, we are going to zoom into a specific longitude region, namely the Pacific in this case. We need to prepare our data, so once again, we are making that JMUN array from the list of 12 times the NP range of 0 through 68. We're going to access that clim mat matrix, and we are going to create it. We are going to create this Climat matrix with np.zeros, and it will have a shape of 144 by 73. Going into that Climat matrix that was just created, we're going to be taking the mean of our pre-CNC on every J month in the jth by ith index and storing it in our Climat matrix. Making a ANO mat matrix from that pre-NC with index 420, all rows, all columns, minus that Climat matrix we just created, but we do need to transpose that Climat matrix in order to subtract these matrices. We're going to suppress our values into the -5 to 5 range using the highlighted for loop. We're going to allow mat diff to equal the ANO mat we just created, setting up an int1 variable from the np linspace -5 to 5 with 81 values. Lastly, going into figure 9.12b, we're going to set up our figure using that Plt subplots, accessing that subplot, setting our central longitude to 250, plotting our coastlines, and setting our table in that highlighted text. Plotting the data from long -180 on our lat variable with that mat difference as our matrix for our contour plot. We're going to have levels equal to that int1 variable created above and our color map dictated by mycolmap. Very similar as above, we are going to add our color bar and labels, which are all of those highlighted lines you see on the screen. Setting our tick parameters with a length of 9, width of 1, adding a little bit of text over our color bar, and wrapping that in a fig.show. We do get this beautiful January 1983 surface air temperature anomaly plot to pop up. We can see that we have zoomed in on the United States using the mat diff matrix. Before I would like to close, I just want to remind us all that when you access the netcdf files, it is good practice to close them at the end of your script so they do not get modified within your code. This concludes Part 2 of Chapter 9, Python Graphics for Climate Science. Join us next time for Chapter 9, Part 3.